Hello, I'm Henry. Welcome back. I'm going to go through some code I wrote here. This is the code I wrote for modeling some of the data from Cassini with regards to Titan's ionosphere. This is the undergraduate research project that I actually did with Dr. Snowden. All the code is my own, though. There's a lot here. There's a lot here, trust me. All three of these files are part of it. So we're just going to go through it by what it is. And again, this is just me practicing explaining my code and hopefully teaching a little bit. So hopping right into it, what we wanted to look at, the data is at a wacky altitude. I think it's like 900 to 1900. That's kilometers, by the way. And we wanted to look at specifically 800 to 1400 with a step or 10 kilometers between each step. So that's what this is. This is the altitude that we actually cared about. This production scalar, I'll get back into later, but it's the production of sort of the chemicals in the ionosphere. The sort of reactions, another way to sort of increase or decrease the speed at which they're happening. From there, we have some data. This is some of the data that's just taken straight from the mission. The reason we declared this altitude and we still want the data from the mission is we are going to take the data from the mission and extrapolate that curve to the altitude range that we care about. And that's what happens here. So we get some data from the N2 data. We take the data we want at the altitudes that we want, which there's only 46 of them. But we take that data, we store it, and then we apply a polyfit to it, and an exponential to that polyfit to get the sort of curves to it. But we're going to do that with quite a few different chemicals. I think we do it with CH4, and I think we do it with... No, we just do it with CH4. But from there, we can create a fit and then have a function that we can apply any number into and get the value of the density at that altitude. That's what this data is density data. And by extrapolating it, we can get it at any altitude we want, rather than just the altitude that the data itself provides. We do the same thing with the CH4. We take in the data from the Excel sheet, we store it, we polyfit it, we exponentiate it, and then we store it as a fit as well. Then we come to H2. Same thing. Same thing we do here, where we have a set of data at a range we don't want, and we can use the sort of trends in that range and expand it to the range that we do want. Now we have data, which is the culmination of all the data. These different H2 datas or CH4 data, these are the data specific to those elements, to those chemicals. Data contains everything. This is everything. I narrowed down these into separate files strictly for nitpicking, sort of just filtering through it with more efficiency, so I could look through it and debug or add things or whatever I wanted. From there, we can add in our other chemicals. The reason we aren't having to read them in this wonky way is because we just have everything in the exact way we want it. We don't have to do all that filtering that we had to do with H2 and CH4. So we can just plug everything in, we can interpolate it, we can do the polyfit, we can exponentiate, all that fun stuff. From there, we have this N constant. This was in some of the literature by Icarus. No. It was in one of the papers we read that you can learn about in my source presentation. I'll have a link in the description. But this is one of the constants that was listed there. Z is just a counter that we're using. And then we go through and store all of these values that we got from interpolating, extrapolating, all that fun stuff, all the work we just did above, and we put those values into another array. This array is going to be split into two parts, the real parts and the imaginary parts. The reason we have a real and imaginary part is we're looking at a wave. Waves can be split into exponentials. The exponential that describes a wave can be split into real and imaginary cosine values, which we do later because it's a lot easier to work with. So we store them in as real values and as imaginary values. All of our imaginary values are starting at 0. It's just so much easier that way. And you can't have imaginary density. So we just set it all to 0. These are the values we found before. This number here, and the reason, even though this says C2H4 and we're using N2G, this is the mixing ratio that we found in the papers as well. So we use the N2G apply mixing ratio, and we get the density of C2H4 or HCN or whatever else we're looking for. When we store everything in this array, we then want to look at a time span to plug into AtmosMech using an ODE solver. I'll get into what AtmosMech is really soon. But the time span is sort of the big handicap in this. This code runs really, really, really slowly. Like, I have turned it on, gone for dinner, and come back and it wasn't done yet slow. So by being able to change the time span, we're able to debug it by making it a very, very small time span, like a time span of 5 seconds. That will run reasonably quickly. But to see any real chemistry happen, any cool things in the graph, we want to look at the code as it goes to a higher value, a higher time span. 2000 is around the length where things sort of smooth out and they don't change as much as rapidly. So we usually stop at around 2000 just for the sake of not having it run forever. So then we plug it into AtmosMech with our time span, our CNOT that we just declared above, and use an ODE solver. What AtmosMech S1 is the code without a wave. I'll explain that soon. But both of these, AtmosMech and AtmosMech S1, are very similar. I'm going to go through AtmosMech 15, it's version 15, because this is the one that is the one with the wave. This is the one that's interesting. So again, we have our altitude. Excuse me. We have our percent reductions that we're going to be using on the fits that we declared earlier, and here are all of our wave parameters. These amplitudes are our percentage, so the wave has an amplitude of 50%. If this was a value of 1, it would be an amplitude of 100%. We're looking at some pretty fast-moving waves, and this is pretty much all comes from the wave equations. So what we want to do is then read in all of the data from the array we declared before, this CNOT array, which is declared here, which we're storing all of our initial densities in. We store all of our initial densities, and we also update everything as a real and imaginary value. The reason the imaginary values are down here is because we want to guarantee that they are 0. They have to be 0. So even if we goof something up over here and I type in like 1 here, it will always be 0 over here. So that's just a little bit of a safety measure. We also update our wave values, our omega values pretty much, our W values, because we'll have a real and imaginary part to that as well. From there, we use a bunch of chemistry. This is again declared in the texts that we read. You can read more or learn more about it in the source presentation, link in the description. But these are pretty much just all for chemistry. These are percents, these are rate constants, as I said in my comments. And we only care about 3 different elements or chemicals right now, which is CH5+, HCNH+, and C2H5+. The P stands for plus because it's a lot easier than writing this every time, especially in code where it would, where it would read that as an addition. So I just keep it as a P. So with all that, we're able to write out these rate constants, these rate laws. We want to have real and imaginary, and because of that, we have to do some funky multiplication, which leads us with having real and imaginary terms in both the real and imaginary terms. The reason I don't have an I multiplier here, normally in an imaginary term you would have an I multiplier, is that it cancels out. This would have been a negative, but the i's times the i's cancel out, and we don't want to have the I there, because that wouldn't work for our code. So we just treat everything as the imaginary. Sorry, the i's would cancel out in this positive, and that's why that's negative there, because I times I is -1. And the reason we leave it out in the imaginary is because we're already declaring it as imaginary. We don't have to say it's imaginary by adding in another I. So we have these rate constants, or rate laws, for CH5+, HCNH+. We left out this one because the literature said it only contributed less than 5%, and if we were to include it, we would have to introduce 2 or 3 new chemicals, which would have to be included in this, which would have to have all their own rate constants written out, so we just skipped it and just said it's 0 because it made it easier. And then we do it for C2H5+ as well. From those rate laws, we're able to get up mass balances, which is pretty simple. You just add the rate laws together. From here, we are including the fit value from N2R+. This is because we have it being produced by the ionization in the atmosphere. So we have to include it as well, and this is where we introduce the wave. with our sine and cosine. Sine, again, being associated with imaginary, and cosine being associated with the real values. Because of the way we're doing this, we're doing the middle function to get the waves this is an ODE function, so we're looking at a differential equation, and we're using the middle function to look at that differential equation. So this is pretty much the ye good old middle function. We have to then do the end terms going forward, and we have to do it backwards as well. So that's what this massive bunch of chunk of code is all about, is just doing the middle function. So once we're done with the middle function, we bring back in that wave, we apply it again into our mass balances, and then finally, we can spit out whatever densities we have at those altitudes, which will be stored in DC. That's where the differentiality comes from. We just call it DC. Atmos-Mech S1 is pretty much the exact same thing, except there is no wave. We set the wave amplitude to 0, and we set the wave parameters, or the wave equations themselves, to 0. Everything else is the exact same, except there is no wave. So, coming back to Titan Atmos, we run Atmos-Mech S1 first because we want to look at, if we just ran it with the density data we had, then we would be starting with some densities that might not be as accurate as we want. So by running it without the wave first, we get it to do all its chemistry, we get it to even all out, and then we can apply the wave. So we aren't just making any leaps with the chemistry. So we take that density data without applying the wave, we store it, and then we store it again into our C0 value, again setting everything imaginary to 0, and then we run it through again to get our final outputs. We are plotting this here. The reason I just have it here in the middle is so that we can look at it without the wave. Very clearly, it's obvious to see what it is without the wave. But then we run it through Atmos-Mech V15, we include the wave, we finally get all the outputs, and then we can plot it all. And the plot, let me just switch the window capture here. Looks like this. We can see very clearly the waves in the atmosphere. We can see some funky waves, which means we did something cool. We did something good, which is super rad. But that's it. Thanks for watching. I hope you had a good time. Hope you learned something, or I don't know, enjoyed me talking to you for some 13 minutes. But if you have any comments, concerns, questions, please feel free to drop them below. Again, I'll have the link to the source presentation where I talk about more about the science of what this code is doing in the description. If you want to watch that, feel free to watch it. But until next time, thanks, bye.